Okay, so what did we study in the last class? Okay, so we asked this question of when does this A inverse exist, right? Inverse of a matrix exists. So in order to answer that, we looked at various things, right? For example, we looked at what is known as the kernel, right? So AX equal to 0. So if you have an X such that X not equal to 0 and AX equal to 0, then the matrix A cannot be invertible, cannot be inverted, right? And also we looked at various other algebraic manipulation when it comes to matrices. For example, if you take the product of two matrices and look at the ijth value or ijth entry, then it's given by summation over all L, AI, L, B, L, J, right? So that's how we write. And similarly, trace and few other things. And then we looked at matrix transformation, right? So suppose AX equal to B is the equation and you want to solve for X, then I need to know what is A, what is A inverse, right? So supposing if I could transform this A into some matrix by making a series of what is called elementary transformation, right? So what is elementary transformation? Can somebody tell me? What is elementary? Huh? Right? If you exchange rows, then that's an elementary operation and it's invertible. Okay, what else? Scaling a row is also an elementary operation, it's invertible. And then replacing a row by a linear combination of that particular row and other rows, right? So that is another linear, elementary transformation. So supposing if I can sort of sequentially transform this matrix A into an identity matrix using elementary transformations, then I can go backward also. That means I can write the product of elementary transformations times A is identity. So you know what the inverse is, right? So we looked at one example also towards the end. How do you get to identity matrix? And in doing so, we did some sequence of elementary operations. Elementary operations correspond to multiplying by a particular matrix, right? So all that you have to do in order to compute the inverse is what? So look at the product of those matrices, right? In some sense, right? You know how to find the inverse. And we also finally looked at a few properties of inverse. Product AB whole inverse is B inverse A inverse, which is again easy to see. A transpose inverse is A transpose inverse is A inverse transpose, and so on. Okay, so then we saw, well, what next, right? So towards that we briefly talked about closeness, norms, inner product, and so on. So we will look at a few other things and come back to these closeness notions today. Okay, so let's get started. Any questions? Okay, so before I start, there will be an assignment which is scribing the notes, right? So what we are going to do is pick randomly 3 of you and ask you to scribe certain lectures, right? Or a particular lecture. So there is a whatever TS have scribed notes. I think lecture 0 and lecture 1. You can go through that and you'll get a fairly good idea. So the idea is you have to go through that part of that lecture and or your notes, whatever you have to scribe. You have to basically explain what is being taught in the class, and you can use your own ideas, whatever. Okay. So one thing is if 2 students copy, for example, there is like more than 60% overlap, even in terms of English, everything, then you'll get 0. Okay. So don't come cribbing to me, regardless of who. So even if you had given your LaTeX code to the other guy, you will also get 0. So be careful with that. Okay, 0 in the sense 0 for that assignment. Okay, so remember it costs you 10 marks out of 100 towards the end. Okay, so let's get started. So today I think TS will send out an email for those 4. It's random. You wouldn't know beforehand, and you wouldn't know unless all of you collaborate. You wouldn't know who the other person is. Okay, so let's get started now. So now we also looked at not in the last class, the class before that, we looked at what is known as the subspace, right? So what is a subspace? If you take R2, R is a subspace, right? If you take R3, R2 as well as R, both are subspaces, right? So what are the properties of a subspace? Suppose you have a set U contained in V, right? V is a vector space over R or C. And I say that U is a subspace of V. When do you say that? First of all, it should be contained in V, right? So it should sit inside V. And then it should be closed under linear combination, right? So if you take any two vectors and alpha beta, if you take alpha beta linear combination of those two vectors, it should belong to the set, right? Closed under linear combination. Okay. So now let's look at a particular set. Okay. So let you take a matrix. Okay. I'll take a very general matrix, which is M cross N, right? This is an M cross N matrix. Now I'll take the following set. Okay, so I'm going to look at all those X in Rn that gets mapped to 0 under A. So okay, so what is this set? Can somebody think of what kind of set this is? So it is that portion of Rn or the vectors which gets mapped to 0 under A. Right, so pictorially this is how it looks like. So for example, this is your Rn. It gets mapped to Rm, right, under A, because it's M cross N. If you write multiply by X, you get an M cross 1 vector, right? So it gets mapped to Rm. Now 0 is sitting somewhere here, so this is your 0. Okay, so there is some small subset here of vectors which gets all of these vectors get mapped to 0, right? So obviously this is a subset of Rn. Do you agree with this, everyone? Of course, it is all those vector in Rn that gets mapped to 0. Therefore, it's a subset of Rn, right? So now let me call this, let me give a name for this. It's called null of A, okay? Because it is those vectors that when operated by A will give me 0. That's why it's called null. Okay. So what can you say about this set? Definitely, if this set is only 0, it contains only singleton, just 0 vector, then we can hope to invert A, right? First of all, even if M equal to N, you can hope to invert A. Otherwise, if this is not just a singleton, let's say it contains few other vectors also, then definitely A is not invertible, right? That is very clear. So what can you say about this null of A? It's also a vector space. In other words, null of A is a subspace of Rn. Okay, so claim null of A is a subspace of Rn. So how do you show this? How do you show? Well, this is what we have, right? So it's a subset of a vector space. If I have to show that it's a subspace, all that we have to do is show that it's closed under linear combination. Okay, so that's easy, right? So how do you prove this? Proof. You take any two vectors and two numbers, right? Let's say uv belong to let's say null of A, and alpha beta belong to R. You take two numbers and two vectors. Need to show that the linear combination, that is alpha u plus beta v, belongs to null. That's all I have to show. Now, can somebody think of a proof? How do you prove that this is true? See, A is matrix and it's a linear transformation, right? So I can replace A by any linear transformation. That's what you would have studied in your linear algebra, right? So they always like to think of these things as transformations, not really as matrices, right? Although it turns out that both are same in this case. Yes? Well, what can you say about U? U is in the null of A. That means AU is, what can you say about AU? 0, because U is that vector which gets mapped to 0, right? So this is 0. What can you say about AV? 0, right? This is because of the fact that U and V belong to null of A. So this means AU plus AV, sorry, alpha times AU is also 0, beta times AV is also 0. Do you agree? Right? So now what does this imply? This implies I can push alpha into inside, right? So alpha times U. U is a vector, alpha is a number. I'm just scaling it, still 0, right? A times beta V is also 0, right? What does this imply? If I add them, I should get 0, right? So A times alpha U plus A times beta V is 0. Well, A is a linear transformation. So A alpha, A V plus let's say U is A times U plus V, right? So it's A times alpha U plus beta V equal to 0. That means, well, this is also a vector, right? Do you agree? This definitely belongs to Rn, right? It's a n length vector. So this definitely belongs to Rn. Now I'm saying it is that vector which gets mapped to 0, right? So what does that mean? This is easy, right? It belongs to null of A. So null space is a subspace. Okay, this is something that you should always keep in mind. Is that clear? Any questions? Okay, so now we know something about the null space, right? So let me look at the picture again. So you have this Rn. Okay, so you have this Rm here. And now I looked at some subspace here, right? This subspace. All of them get mapped to 0, right? 1 point, right? This is a subspace. Okay. Now, if it is a subspace, it's a vector space. So I'll have a basis, right? Do you agree? So let's call this basis as V1 through V. Let's say K. Okay. There are K vectors. That means it's a K dimensional subspace. Suppose. Okay. K could be 1 to any number less than or equal to n. Okay. So now you have this vector space and you have the basis. So now if you look at the entire Rn will also have a basis, right? So now the question is, can I add a bunch of more vectors to this to get a vector space of the entire Rn? Is that clear? Is that fine? Can we do that? For example, you have R3. R2 is a subspace. You have a basis, right? What is the basis for R2? When viewing it as a subspace of R3, what are the bases? So suppose you have this, right? So, right? So now if I look at R2 as a subset or a subspace of R3, then this is 1, 0, 0, right? This is a standard basis or standard vector, right? This is 1, and if I call this as my xy, this will be 0, 1, 0, right? These two are basis for R2. But if I want to get a basis for R3, what should I do? I should add one more element, right? What is that? 0, 0, 1, right? If I add this, I'll get the basis for the entire space. Right? Similarly, if I have a null set or null of A, which is a subspace, I have a basis, which is this. Now, what should I do? I should add a bunch of more vectors to get a basis for the entire space. Do you agree with that? Okay, so now I can do this, right? So V1, well, by the way, I'm really sloppy here, but we should be okay, right? And I can add, let's say, vectors like U1, U2, etc., UL, okay, to get the basis for Rn. Well, K plus L should be equal to N, okay? So otherwise, this is not true, right? I'm going to add more vectors so that the total number of bases is equal to N, which is the dimension of Rn, right? Is this clear? But how do you prove that this is true? Well, do you remember replacement lemma? How many of you know replacement lemma? Meanwhile, I'll check if everything is fine here. Okay. So what is replacement lemma? I have two sets of bases, right, of a vector space. I can keep on replacing this by one of these, replace this by one of these, and keep on doing that, right? Until I exhaust the entire thing, I'll replace, right? Do you agree? So similarly, can you think of this extension as a replacement? So for example, I have a set of bases for the entire Rn, right? And I have a basis for the subspace, right? So what am I going to do? I'm going to take one of the elements in Rn, replace it with one basis of the subspace. The second basis I'll replace, third basis, and so on. I'll replace everything, at least a bunch of it. Now what do I get? I still have a basis for Rn, right? So now a part of it is a basis for subspace, and the remaining is something that I have added. I can think of it like that, right? So replacement lemma will be useful here. You can show that, you can extend. I'll leave that as a homework. You should think of how to do that. Okay, formally you should be able to write. Okay. Anyway, so this is the entire space, right? So I can extend this. Okay. Now with this, let me state a few more names that people use in matrix theory. So let's say image of a matrix. Well, I can always remember, I can always replace the matrix by a linear transformation T. Okay, so I can rewrite the whole thing with the same T. Just in LaTeX, if I had LaTeX all this, if I take all your notes, say control R, I replace capital T by capital A by capital T, you're done. So you'll get a linear algebra textbook, right? So what is the image of this? Well, pictorially, let me see what is the image of this, right? So this is, I'll write it in general fashion. So this is a vector space V, and this is a vector space W. What is the image of this? So essentially, there is a mapping which maps V to W, okay? Now you take each vector and see what it gets mapped to, right? What happens is if you exhaust all the vectors in V and see what it gets mapped to, maybe it gets mapped to some subset here, right? Right? If this subset is entire W, then great, but otherwise it's some subset here, right? Do you agree? So this set, I'll name it as image of A, right? Image because you know why it's an image, right? It's like you shine a light and whatever. Okay, so right. So how do I write this? It is all the vectors here, right, in W, right? So what are those vectors? It's AV such that V belongs to V, right? Right. V is a vector in V. I'll see what happens when I operate A, right? So it takes where in W. I'll collect all those AVs, right? That will give me the image, right? What can you say about the image? Is it a vector space? See, all those vectors which gets mapped to 0, we saw that it's a subspace. It's a vector space in itself. And now I'm going to take all the vectors and it's mapping. So is it a subspace? In other words, is it a vector space? So definitely this is a subset of W, right? Very clear, because obviously A cannot take a vector and map it to something outside of W. That's not possible, right? So now, is this a subspace? Again, I have to do the same logic, right? What can you say about this? How do you prove that this is a subspace? Huh? Linear combination, I think one more thing you have to verify, the 0 gets mapped to 0, but it's trivial here, right? So anyway, so how do you prove this? So I have to take a linear, let's verify if it is true. I have to take two vectors in A, right? Image of A, right? So I'll write it, I'll write it as a claim, okay? So image of A is a subspace of W. Okay, I'll write it as question mark because we don't know. We will see if it's possible. Let's look at proof again with a question mark. If it works out, then I'll remove the question mark. Okay. Now what should I do? I should take two vectors in image of A, two numbers, take a linear combination and show that it belongs to, right? Same step. So let you take V. Let me not use V here. Okay. So what should I do? Yeah. So let's say W1, W2 belongs to image of A. Okay. You take two vectors in the set, two numbers, alpha, beta belong to R. Well, if your vector space is over C, then alpha, beta belongs to C. Okay. Now you take these two vectors. What is it that you need to show? You need to show that the linear combination belongs to the image, right? Okay, so what does W1 belong to image of A means? It essentially means there is a vector V1 or V in V that gets mapped to W1, right? This implies there exists a W1 belonging to, sorry, let me use V1 belonging to V such that AV1 is W1. Okay. Similarly, similarly, W2 belonging to image of A implies there exists a V2 in V such that AV2 is what? W2, right? Now I can write linear combination of W1, W2 in terms of AV1, AV2, right? So this implies I have to write alpha. I'll write it here. Alpha W1 plus beta W2, okay, belong to. This is a very sloppy way of writing mathematical proof, okay, but I want you to correct it when you scribe it. You have to write it precisely, okay. You probably have to write it in the reverse direction. Okay, so this I need to prove that it belongs to. I'll write it as a question mark. Is this true? Suppose this is true. Well, this is also true, right? All that I'm doing is substituting, nothing else. Okay. If I verify that this is true, then the previous statement is also true, because all that I have done is substitution. So again, I can do this, right? A alpha V1 plus beta V2. Linearity of this belongs to image of A. Question mark. Now, can you complete the proof now? What can you say about this? This guy. It belongs to V because V1, V2 belongs to V. By property of vector space, this belongs to V. Now, what can you say about A times this vector? It should be in the image, right? So this is right. Therefore, this is right. Therefore, this is right. Then we are done, right? I'll leave it for you to write a rigorous proof. Okay. Right? This gives you the idea. The moment you know this, then writing a rigorous proof is like cakewalk, right? Okay. Now, what do we have? We have the image and we have the other part, which is the rank, sorry, the nullity, right? So, or the null of A, right? Both turned out to be subspaces, right? One here in the image, the other one is the range, right? Okay. Okay. So now let's look at one thing. So which is what is known as, it's a very important theorem in linear algebra. How many of you have heard of rank nullity theorem? Heard of it? No, you should have heard of it in linear algebra, right? Yes or no? It's okay. I don't bother you. You can say, at least, can you raise your hand if you have heard of rank nullity? Okay. Anyone know what rank nullity is? Can you tell me? Yes. Do you know what rank nullity is? The dimensionality of the, right? Okay. So how do you prove that, right, is the question, right? So how do you prove? I'll give you a pictorial, slightly pictorial proof, but again, you can convert that into very rigorous proof in a very straightforward manner. Okay, so now let me not state the theorem. Let's see what we can see. Now, I'll write it in a very general form. Okay, so I won't write it as matrix and some RNRM. I'll write it as transformation VW. Okay, so this is a vector space V and this is a vector space W. Okay, and you know what nullity is, right? Null, and there is a transformation, or you can think of transformation as matrix, right? So what is the null of T? It is all those vectors which get mapped to 0, right? So that is some subspace here, right? So I'm sure it will get stuck, I guess. Okay. So now if this is your null space, which gets mapped to 0. Okay. All these gets mapped to 0. Okay. This is a subspace. Okay. Now, what can I say about this? Since this is a subspace, I have a basis, right? So let me call V1, V2, etc. Vm are the basis. Okay. By extension theorem, or it's in other words replacement, I can extend this to the entire space, right? I can make this as a basis for the entire space. I'll add a bunch of other vectors um or un such that this is a basis for, maybe I'll write it in different colors, u1, u2, etc. un form a basis for v. This is clear, right? Okay. So of course tv1 is what? 0, right? tvi is 0 for all I 1, 2, etc. m. This is very clear, right? It goes to 0. Now let's look at what happens to tu1 through tun. What can you say about that? Yes. So what can you say about, some tun or tu1, tu2, etc. tun? I know what happens to tv1, tv2, tv1, right? It will give me 0. What happens to this? This definitely doesn't give you 0, right? For sure, right? 0 does not belong to this. That's something that we know, right? But what can you say about this set of vectors? Can you think of something? What are the, the moment you see a bunch of vectors, what is the first question that you can ask? What are the things that we have studied so far as vectors are concerned? Huh? Don't hesitate. You can just, even if it's wrong, it's okay. Nobody will feel bad. Okay? Huh? No, a bunch of vectors cannot form a vector space, right? I'll give you 2 vectors. It cannot form a vector space. What can you say about 2 vectors? Linear independence, right? Basis is the next question, whether it forms a basis or not. But linear independence is the question, right? Is it linear independent, right? So is it linearly independent? How do you verify this? Let's verify. Okay. So how do you verify that this is linearly independent? Huh? Well, all that I have to do is take linear combination of these vectors, any linear combination, equate it to 0, then the coefficient should be 0. Do you agree with this? Okay. Now, suppose, right, let's say alpha 1 t u1, right? Yeah, so tu1 plus alpha 2 tu2 plus alpha n tun equal to 0. What can you say about this? Let's do reverse engineering, right? We don't know what. So if they are linearly independent, alpha I should be 0, right? Clear? Now, what does this imply? By linearity, I can push alpha 1 inside, alpha 2 inside, and so on, right? Again, by linearity, I can add them. So I'll write directly this thing, right? Suppose the first one is, this is true, then this is also true. What does this imply? Right? So in other words, both ways, right? So if this is true, then this is also true, right? That's what we have. So what can you say about this now? Looking at this equation, what can you say about this guy here? It's linear combination of ui's. So what can you say about the linear combination of ui's? Huh? So ui's, of course, it depends. So here are the ui's, right? So it's definitely not in, I mean, it's definitely in V, right? Each of these ui's are in V. A linear combination of ui's should be in V, because it's a vector space closed under, right? So this belongs to V for sure, right? But now what is it that I'm saying? I'm taking an T, operating it on a vector in V to get 0. What can you say about V, this vector? Ui should belong to, can it belong to null of T? No, why? Right, so it's formed the basis, and we already considered the basis for null and extended it. So this cannot span the other, right? So it cannot be, definitely this cannot be in the span of or in the null, right? What are the other choices now? Huh? The only possibility is this is 0, right? So this implies, but UIs are linearly independent. This implies alpha is 0, right? Do you agree? So that means they have to be linearly independent. Okay, is that clear? So now when you write the theorem, how do you write the theorem? Of course, theorem is clear. This is, so now this is a linearly independent set, right? Now, what are these? These are nothing but TU1, TU2, TUN forms a basis in W, right? Do you agree? It forms a basis in W. Now, suppose I take a vector V in V such that TV is not 0, right? Then I should be able to write this as a linear combination, right? Do you agree? Okay, so the second claim is, don't worry about this. I'll just write this. Also, for every V not in null of T, TV can be written as linear combinations of TUI. Okay, right? That's also possible, right? So now, what does that mean? That means, okay, think. I'll write it as think. TU1, TU2, etc. TUN spans image of T. Okay, you know what image is, right? It spans the image, and it's linearly independent. What does this imply? Basis, right? Forms the basis for image of T. Now, this forms the basis for image of T. So there are n vectors, right? And now there are m vectors which span the kernel of T, right? When you add them, when you add all of these, you get the dimension of V, right? M plus n is the dimension of V, but that is nothing but dimension of nullity of V T and plus the dimension of image of T, right? So, okay, now I deliberately I've been a little vague here so that you'll go back, those, at least those who is supposed to scribe will go back, think about it and write. Okay, so this implies dimensionality of null of T plus dimensionality of image of T is equal to m plus n, right? Okay, so now let's see. So this is what is called rank nullity, right? Where is the rank and where is the nullity? Nullity is very clear, right? So null of T is all those vectors which gets mapped to 0, Ax equal to 0, right? Is the null. Okay, null. What about this? Can you say something about this? Suppose T is a matrix, right? So what can you say about this? What is image of T? First, let's try to understand that. What is image of T? It is all those vectors which gets mapped to a non-zero vector, right? Something like Ax is not equal to 0, right? Do you agree? So such vectors, you take any vector x, you take Ax such that it's not 0. So Ax will be the set of all such Ax's will be your image, right? Now, what about null of T? It is all those x such that Ax equal to 0, right? So that means I'm looking at basically the linear combinations of columns, which gives me 0, right? Do you agree? You are not supposed to use mobile phone inside, okay? So please don't switch off your mobile phones, right? So now this turns out to be, maybe I'll do one thing, I'll just state it, think about it. If you have any questions later on, maybe in the next class, I'll try to answer. So this turns out to be what is called the rank of A. Okay. What is this called? Nullity of A. Okay, null of A. Okay, so this is equal to dimension of the entire vector space. It's n, or whatever the dimensionality of A is. Okay. So that's why it's called rank nullity theorem. It's essentially this. Okay, so the only thing is think about this also. Why it's called this thing. What is rank, by the way? Number of linearly independent columns, right? Well, it turns out that it's also equal to the number of linearly independent rows, right? So let's try to, I won't rigorously prove, but I'll try to convince you that that is the case. And I will refer you to the notes, wherein notes meaning Savan had shared a link to my notes, right? There is a very elegant proof of, or very similar proof, okay? So now let's look at that result. So row rank is number of linearly independent rows equal to column rank, that is the number of linearly independent columns. That's what we defined it to be, rank, right? Okay, so how do you prove this? Any idea? How do you prove this? How do you actually prove? How do you prove that row rank equal to column rank? Oh, that's what I'm saying. That's what you're supposed to prove. Row rank means rank of A. I mean, in terms of the rows. Okay, if you are defining your rank as the number of linearly independent columns, then rank of A is the number of linearly independent columns. Rank of A transpose is the number of linearly independent rows of A, right? So rank of A equal to rank of A transpose. That's what, okay, so good. Let me also write that. It's rank of A, which is equal to rank of A transpose. So how do you prove this? Okay, so let's look at this. Okay, so I'll give a simple, let's look at this through an example. Okay, so let's say there is a 3x3 matrix. I'll write the columns as A1, A2, A3. These are the columns. Now, if I have to write this as linearly, so what is rank of this matrix? Number of linearly independent columns, right? Suppose the number of linearly independent columns of this matrix is 2, not 3, right? 2. It's rank deficient, right? The rank is not 3, it's 2. So now if it is 2, suppose, let's say, V1 and V2 are the basis for the columns. That means you take any column vector, I can write it as a linear combination of V1 and V2. That's what it means, right? So what does that mean? The first one, I can write it as, let's say, alpha 1, alpha 1 1 V1 plus alpha 1 2 V2. Okay, this will give me the first column, right? Do you agree? What about the second column? A different linear combination. So maybe I'll write it as alpha 2 1 V1 plus alpha 2 2 V2, right? I can write this. Is this visible properly? Yeah. Okay, last one is alpha 2 2 V1 plus alpha 2. Oh, sorry, did I write 1 1 1 2 2 1 2 2 3 1 3 2? Okay, I'll get this, right? Same, these both are equal, right? So, okay, now can I write this in a slightly different fashion? What am I doing? I'm doing a linear combination of columns, right? That's what I'm doing. So what kind of, suppose I want to take a matrix and consider linear combination of columns, what should I do? Multiply by a vector, right? The coefficient will give me this thing. Do you agree? So that means if I take V1, if I take V2 and write it as alpha 11, alpha 12, what do you get? This is like AX, right? AX will give me linear combination of column. Remember, I think I had shown that earlier, right? AX is basically linear combinations of the columns of A where the coefficients are given by the entries of X, right? So entries of X are alpha 11, alpha 12, columns are V1, V2, right? So this will give me the first entry, right? Do you agree? So what happens to the second entry? It's alpha 21, alpha 22, right? That will give me the second entry, which is this column, right? What happens to the third? I don't know, maybe orange. Alpha 31, alpha 32, right? This will give me third, right? So basically this whole matrix, I can write it like this, right? So let's look at this. Let me call this as C matrix and the other one as just give me an alphabet. No, so what should I should call this as A. I'll call this as C, and then this coefficient matrix, right? So what should I write? Maybe R. Okay, I'll call it as R, right? Do you agree with this? Fine. Okay, so basically what we have is A, I can write it as CR. The columns of C are linearly independent. R will give me the coefficients, right? Okay, so now what can you say about the rank of A now? So in terms of C and R. So definitely the column rank is 2, right? In this case, 2 linearly independent. What can you say about row? What can you say about row? Okay, so this is 2 cross 3. This is 3 cross 2. Okay. Okay, so what can you say about the rank of this guy? So what can you say about the row rank of this guy, R? 2, right? It cannot 2 or less. Well, it could be 1 also. We don't know, but at least at most 2, not more than that, right? So if the row rank of this R is 2, what can you say about row rank of A? Can somebody think of it? What can you say? What can you say about row rank of A? So it's number of linearly independent rows, right? If the row rank of, suppose, let's say row rank of R is 1 itself, that means this is some 2 times this, suppose. So, okay, let's write that. Okay, so A is CR, right? But R has row rank of 1. So let me write this. R1 alpha times R1. This is what you have. Okay. Now, what can you say about row rank of A? What can you say about row rank of A? Huh? Is it 1 or 2? Can it be 2? Huh? Can it be 2? Yes or no? Huh? Row rank. Okay, number of linearly independent rows. How many linearly independent rows of A you can have? Any guess? Huh? What is that? Sorry. Row rank is 1. Why do you say that? Let's not worry about elementary transformation. So not elementary transformation of R. Okay, so that is also correct. I can do elementary transformation and get 0 in one place and R1 in other place. So what is elementary transformation? That's also something I can write, right? So for example, you have C. What I can do is I can do elementary transformations E1, E2, for example, to get something that is like this, right? So something and 0 here. Do you agree? I can do that. And I can do the reverse, exactly inverse, right? because these are elementary, right? So what I have here is this kind of a matrix, right, with one row not being 0 and the other one being completely 0, right? That kind of a matrix. So now what can you say about the row rank there? I mean, it's clear, right? Intuitively, is it clear? At least I don't want to rigorously prove it. It's not that difficult, but is this clear? It cannot be more than one, right? So essentially, the claim is row rank of row rank of A is less than or equal to 1 here, right? It cannot be more than 1. Do you agree? Well, can it happen? But then you are in trouble, right? So the column rank of this is 2. Can you have a row rank of 1? It cannot be. I'm just giving an example. Okay. So if this is not the case, which let's say the row rank of this can be at most 2, right? Well, this is an example of row rank of 1. But what is in general R? R is like this, right? So R1, R2. So what is the rank of this? Less than or equal to 2, right? It cannot be more than 2 for sure, right? Okay. So in fact, row rank of this is less than or equal to 2. So that means row rank of A should be less than or equal to 2, right? It cannot be more than 2 because row rank of R is also less than or equal to 2, right? So now I have row rank of A less than or equal to 2. Now what should I do? What happens if I do the same thing for A transpose? I can do similar, right? What is A transpose? The columns become row and row becomes column, and I apply the same thing. So you have to fill the gap now. So essentially it turns out that the row rank equal to column rank. Okay. I know that it's little vague here, but I want you to think about this and go through the notes at least once. But you should never forget the fact that row rank equal to column rank. You should never forget the fact that rank plus null is the dimension. Okay, if you have an n cross n matrix, the rank of A plus the nullity of A should be equal to n. N is the dimension, right? So that is something that you should always remember because it's very, very important. Okay, so now I think let's move on let's slightly move away from rank and so on. So I think this is enough information about rank. So let's move on to what is called inner products. Okay, so let's see if something is required in between, we'll go back and try to understand that. But otherwise, we will try to understand what is an inner product. Okay, so this is something, it's an extension of something that you have already studied, right? I think you have studied this in your linear algebra, inner product. Yes. Okay, so what is the use of inner product? Any use? Or is it useless? Have you ever used inner product in your other subjects other than linear algebra? Other than math, by the way. At least one branch. Then we should suggest removing linear algebra and math, everything, right, from this syllabus if you are not used any of those. So okay, let me start with electrical because so any courses where you have looked at inner products? Okay, are there any electrical engineering students? Please raise your hand. It's okay, you can raise your hand, not like, okay, good. So yeah, you guys should answer. Never heard of inner product or never used inner product in your electrical engineering curriculum? What about computer science? What about mechanical? Computer science may not have used. I don't know. Have you used? Mechanical, I'm sure you should have used somewhere. Okay, forget it. So what is the use of inner product? What does it give us? If I say the inner product of two vectors is very high, what does it mean? Yes? What does it mean? Similar. Will it give us similarity notion? you can think of inner products as dot product, right? So you're saying dot product is very high. When can it happen? For example, you have these two vectors. Yes, inner product will be very high. What about, for example, this vector? Almost, let's say 89.999 degree. What is the inner product of or dot product of these two? Very low, but it depends on the length of these two vectors, right? Length could be 100 billion and 100 billion. Then inner product is not, the dot product is not low, right? It will give some very high dot products, right? So inner product or dot product doesn't give you similarity in that sense. The number, the absolute value will not give similarity. So when will it give similarity? Huh? See, the length should not be exorbitantly high, right? So you should standardize length. In other words, you should normalize length, unit vectors, right? Then talk about dot products. Then it makes sense, right? So if the dot product is high, that means it's aligned, otherwise it's not, right? But not for any arbitrary vector, okay? Now let's look at how you define inner dot product, right? So if you have two vectors, let's say x1, x2, and you have another vector y1, y2, this is the dot product. Do you agree? Right? So I'll write all the vectors as column, okay, from now onwards. Every vector I'll think of it as a column vector, not the row vector. So what happens to this? Suppose this is, I call the vector as x. This is x transpose y, right? Do you agree? So this will give me an dot product, because actually dot product, right? So now, what are the properties of dot products? Let's look at let's list some of the. At least quickly go through that, and then I'll stop. I think it's almost, we have only 2 minutes. So this is linear in x. Do you agree? It's linear in y, right? If I take x transpose x, it's always non-negative. It's equal to 0 if and only if x equal to 0, right? Equality if and only if x equal to 0. What else I can say? X transpose y is same as y transpose x. Do you agree? It's the same thing. It commutes. So these are the properties, right? Now, if I have to write a book, of course, I can write a book on dot products, right? Then let's say you talk about some other kind of dot products, right? Then I have to write another book and so on. Instead, what I can do is I can generalize this or abstract it out, right? So what is it that you are doing? Dot product means you are taking two vectors and you are giving me a number, right? So it's a function, right? It's a map. It's mapping two vectors to a number, right? So what are the properties? These are the properties, right? It's linear in the first element, linear in the second element. F of x comma x is always non-negative, equal to 0 if and only if x equal to 0, right? And f of xy is same as f of yx, right? This kind of a function. Now, any function that satisfies these properties, it's like almost think of it as a inner product, right? So, and we will move from there from the next class onwards. Okay, few more classes will kind of wind up linear algebra. Maybe we'll look at 1 or 2 problems in data analysis related to linear algebra, and we'll move on to optimization, which is like the most important part of data analysis. Okay, yeah, thanks.